So let's continue the nice stream of presentations on SumCheck. We have seen improvements on the prover. Let's go with some more improvements on the verifier. And yeah, let's see that.
I think I have this.
I have a mic.
Yes.
Alberto, please, the stage is yours.
Thank you. So hi, everyone. As she says, I'm going to continue talking about ways of using the SumCheck protocol, in particular to improve the efficiency of our recursion in the context of the Jolt zkVM. This is a joint work by Kwang, Sagar, Marcos, Justin, Andrew, and Michael. And this work, even though it applies to particularly the Jolt zkVM, its techniques can be widely used in other contexts. So I think these are not my slides, or at least they are not updated. These are my slides, but they are not the ones I recently sent. Yes, thank you. So we have two different ways of achieving recursion on zkVMs. One is a simple recursion where we prove the proof that we get from a zkVM inside a zkVM. And the other one is wrapping. We compile the verifier of our proof into some arithmetic constraint systems like R1CS. And we want to make the verifier cheap in both, in the case of recursion, while minimizing the overhead of the prover. And as I said, this applies not only to Jolt. So one thing that the Jolt team has been doing for many years now is both applying the SumCheck protocol to many different problems, but also to understand the structure of the computation to make it more efficient. And in this case, in modern snarks, we can see in many different talks this weekend that they are composed by a PIOP and a PCS. And also the verifier computes differently the PIOP and the PCS part of the snark. So in particularly the case of Jolt, we use the SumCheck. So the verifier for the PIOP does these SumCheck rounds, evaluation claims, and all these operations are over the scalar field of the prover. In this case, we call it FR. And in the case of Jolt, this turns out to be around 30 million cycles, which is about 2% of the total of the computation of the prover. On the other side, there is a part of the verifier that operates on the Dory, on the PCS of the snark, and those are group operations and pairing operations, and these are on a different field called the base field, and in particular is non-native to the Jolt prover. And because of this non-native arithmetic that we need to do for these operations, the verifier in the recursion for this part takes 98% of the total. To give you an estimation for a trace of 2 to the power of 20, this verifier in Jolt takes around 1.6 billion cycles. So, as I was saying, one thing that they do very well is understanding the structure. In this case, we have a verifier composed by two different sub-verifiers that don't share an intermediate state. So we can see the PIOP, or the verifier for the PIOP, producing opening claims, and the verifier for the PCS checking them. And each half can be verified independently. So the idea is as follows. We want to extend the initial proof with two sub-proofs, one proving the PIOP and one proving the PCS part of the snark. So in particular, this auxiliary proof, we call it by PCS, certifies that the checks with this PCS are satisfied. So for that, we need a second curve to make it more efficient. And we can compute them in some sequentiality. So we do first the PIOP part and then the PCS. These techniques are different to folding, so we can say that we have some benefits, in particular that there is no IPC, folding accumulator, running instance, and so on, which make BIO more complex, arguably. And of course, we achieve that the verifier of the PCS snark is native to the recursion layer. So just to mention curves that are used in Jolt, particularly, we use BN254 for the prover, and it has a cycle of curves with another curve called cramping. And we want these group operations to be native in the second snark, we call by PCS. And one thing to note is that cramping is not pairing friendly. So that limits our options for which PCS we can use to prove this. In particular, Jolt uses Harax, which is a transparent, and it doesn't need pairings. It's not a pairing-friendly curve. And one thing to note is that the verifier is O to the square root of n. So in particular, that's 2 MSNs of size square root of n. And we are focused in this work particularly to minimize the committed data. And one technique that is widely used in this work is virtual polynomials. So we now are going to construct our PCS. And for that, all these checks that we were talking about, all these group operations and so on, they will become their own PIOPs. And this process will be constructing different PIOPs and then combining them together to some unique evaluation point at some point. So to understand first the operations that the Dory verifier does, we can identify 3 phases. That the first one, we get all this information from the prover, which are group elements, and then it does some operations in sigma rounds that it updates these accumulators, seed, E2, E1, E2, and so on. And then it does one final pairing check. And the PCS snark only proves the first 2, and we leave the multi-pairing as outside this proof to be checked directly by the verifier in our recursive layer. And because it's a fixed, constant number of operations, it doesn't add much to the total cost. In particular, I think it's around 9%. And this table gives an idea of where the cost of these operations land. So we see that all of them are linear to sigma, which is the number of rounds. And we can see that the most operations come from the target group of the pairing. And not only that, but also operations in the target group are more expensive. So we are going to focus on those operations. And just to note that the operations, or the PIOPs that derive from the operations on U1 and E2, just follow standard textbook techniques. They're also on the paper that is upcoming on this work. And we are not going to see them in any depth here. So there are 2 types of operations on the target group. There is multiplication and exponentiation. The target group is basically an extension field of degree 12. So we can represent any element of this target group as a polynomial of degree less than 12. And multiplication is equivalent to this equation with some quotient polynomial and our g, which is the irreducible polynomial of degree 12. And the way we do these things with SumCheck is we encode these coefficients as multilinear extensions. In particular, we use some 4-variate, we will see in a moment why 4, and we create our constraint C, so that we can run our SumCheck for this zero-check PIOP. In particular, the prover shows that this equation holds using the SumCheck protocol. Another interesting approach to how to prove exponentiation we expand our exponent alpha of base 4, and thus we can create this chain of exponentiations. And the way we approach proving GT exponentiation in this work with this PIOP is by packing the entire chain into one single witness row with m plus 4 variables. M is basically the length of the chain, and 4 is the base that we choose. So in particular, for our curve in Jolt, m becomes 7. And the constraint is as follows. If you see the constraint is using the same technique as we saw earlier for multiplication. And you can see that basically row shift is equal to b times row, b times row, yeah, where b is the log degree selector of the 4 elements powers of g. And one thing to note here is that row shift uses this shift sum check and is our first instantiation of how to use virtual polynomials to avoid committing to another extra polynomial. In this case, we don't commit to row shift because we are already committing to row, and thus we don't need to commit to any other element in this equation. And as we did before, we also ran the PIOP, the zero check PIOP, with the same sum check protocol. And why base 4? Because we were saying that the verifier cost in hierarchy is dominated by how much data is committed, in particular is square root of n. It shows here that a shorted trace beats the benefits that we get from some low degree constraint. So we have covered GT, we haven't covered G1 and G2, but you can imagine it's similar with different operations. And now we have all these families, and we also want to check that the different elliptic curve PIOPs are consistent, meaning that the output of an operation will be the input of another operation. And that creates some sort of DAG, or directed acyclic graph, of sum-check instances. And one thing to note in this case is that the graph is quite small, so the verifier can compute it directly. And we avoid extra commitments as well. We avoid other techniques like the grand product polynomial or the permutation argument. So, as we were saying, we are now with these several sub-PIOPs, each one addressing one of these Dory operations. And this PIOP has its own witness multilinear polynomial fi with its own number of variables, which are all different. And after running all these sum checks, each of these polynomials will have a single evaluation claim. And we have C evaluation claims on these polynomials, each of which is of different size. So because we want to minimize data, and because we know how the verifier for hierarchs works, we want to find an optimal way to address this problem. So the first two approaches are quite naive. The first one is committing each of these polynomials separately, and that will make the verifier pay for all these openings, each of which is square root of the number of variables of that polynomial, and the cost of this particular case grows linearly in C. Another naive approach is by padding. In this case, we achieve this one shape, one polynomial, one commitment, but the verifier is also linear in C, and in particular is quite more expensive than we would like. So this work shows a different approach called prefix packing, and we achieve all that we want, which is one commitment, we treat these FIs as virtual polynomials, and the work is less than 2 times the sum of this 2 to the power of ni. So just to dive a bit deeper into what this prefix packing does, we can treat this of each separate polynomials fi with a unique binary prefix, forming a prefix-free code. Prefix-free means that the unique binary element that we use to identify each of these polynomials is not a prefix of any other binary encoding of the other polynomials. And this is unique because of some inequality called Kraft's inequality. So we have our big polynomial f described as follows, and we can put some bound to this size of the polynomial. So once we have that polynomial, now we want to fold these claims into one via these subcube selectors. And the verifier in particular can compute the right-hand side of this equation on its own because it knows the selectors and it knows the claim, and the number of C in particular is small, is around a bit over 100. So for 19 rounds, this becomes a 21 variable polynomial, and it's quite small in terms of coefficients that we can compute efficiently. So just to finalize, we have some results showing the efficiency of this approach. So with the standard verifier, so the standard recursion, the verifier cycles are around 1.4 to 1.8 million for traces from 2 to the 16 to 2 to the 26. And we can see that we achieve almost, when I say we, the authors of this paper achieve almost an order of magnitude of improvement. So where the cycles go. So once we have done all this machinery, it turns out that the most work is left for the openings of the PCS that we use for this secondary auxiliary snark, which is the Hyrax openings. This slide shows that the recursion prover overhead is only 1.3 to 1.8 seconds, and the combined proof is a bit larger, but it's quite stable across all these trace sizes. And one technique that we haven't covered, so far we have been talking about we have been talking about the recursion using the Jolt zkVM. This is now recursion using wrapping, meaning that we compile our verifier to R1CS, and we have different ways of proving that R1CS. And what's interesting is that the number of constraints for this extended verifier is less than 10 million, and is dominated by native field arithmetic. I think the only part that is not field arithmetic is the fixed number of pairings. So just to quickly mention the two approaches, we have option A, in which we wrap we prove our R1CS with Spartan and HyperKCG, and this is quite fast on a laptop for the prover. The proof size is a bit bigger than with Gross16, and the verifier is less than 10 milliseconds. The second option is Gross16. It takes a bit longer for the prover to run, around 7 to 10 seconds. The proof size, as we all know, is quite small, and it requires trusted setup. So the takeaways, again, as I was saying, we get a lot of benefits from understanding the structure of our computation, in this case of understanding the structure of the verifier in a recursive setting. And we extend our proof to a tuple of proofs. And we shift the checks for Dory to the prover. And we also don't need folding. If we want to do wrapping, and we want to maybe proof on chain and so on, we turn out to be, like we come out with 10 million constraints from some L1CNs, and it can be proved via Groth16 or Spartan. If we want to prove this recursively with Jolt, then we drop the verification cycles from 1.5 billion to 200 million. And as I was saying, even though this presentation has been focused on Jolt, we can generalize these techniques with other settings as well. Thank you very much.
Thank you to our speaker. Let's start with some questions. We have time for a couple of questions. Okay, I will start the question session. I have two, actually. I'm wondering about two things. One related to efficiency and one related to security. Are all your efficiency improvements actually benchmarked from, like, for a full implementation of Jolt, or is there something missing?
So the paper shows end-to-end implementation results for this. I haven't seen the code and I haven't run it myself.
Right. And since this is about verifier, we are always worried, or we should be worried, that we may introduce, so once we modify a possibly correct verifier, once we modify it with some improvements, we should be worried about security issues, like how certain are you that the new code you have introduced is efficient but also not buggy?
Anyway, yeah, in the paper they have proofs for each of these reductions.
And do you have like formal verification, or do you plan
Right.
ahead?
I'm sure the Jolt team has a strong effort on formal verification. Probably Suyash also may know more about it, but yeah, at least they have proofs in terms of the source lemma in all these operations for the PIOPs, each of these sub-PIOPs that we have for the different group operations. But I'm sure they also have efforts on formalization.
Okay, yeah, thank you.
Thank you.